Dear friends, welcome to this lecture on abstract algebra. We are studying ring theory. In this lecture, we shall study integral domain. Before definition of integral domain, I have written earlier two definitions. We shall see first these two definitions and then we shall discuss the definition of integral domain. First, let A is not equal to 0 and A belongs to R. A is non-zero element in a ring R, then A is called a divisor of 0 or a 0 divisor. If there is an element, another element B in R ring, R is a ring, B is again non-zero such that A into B is equal to 0. So what is the meaning of this? There are two non-zero elements in the ring R. A is not 0, B is not 0, but A into B is equal to 0. Then we say A is a 0 divisor, also B is 0 divisor or divisor of 0. There are two divisors of 0, A and B, which are non-zero. They are non-zero but their product is 0. So this is an unusual case considered with A, or we have dot here, A dot B is 0. Usually we have for usual multiplication in the set of integers, rational numbers, real numbers and complex numbers. If A into B is equal to 0, then this implies either A is equal to 0 or B is equal to 0. This is the case usual, and here that means the product is 0 implies A is 0 or B is 0 or both are 0. Then and only then the product is 0. This is for usual multiplication in integers, rational numbers, real numbers, complex numbers. But this there exists rings such that there are divisors of 0, and that means AB equal to 0 till A is not 0 and B is not equal to 0. Then these are the 0 divisors or divisors of 0. So see, usually we have this. We have in a set of integers, or in real numbers, and with usual multiplication. AB equal to 0 implies A is equal to 0, B is equal to 0, and this is not the case for 0 divisors. We shall see the example of 0 divisors after defining integral domain. For example, if we consider Z6 as in our earlier lecture of field, this is a set of integers modulo 6, and these integers are remainders obtained when an integer is divided by 6, and these are 0, 1, 2, 3, 4, 5. These are results from number theory, and here the multiplication modulo 6 is defined as, that is I multiplication modulo 6 with j is equal to k, where k is the remainder of I into j divided by 6 on division by 6. And now we may see here there are divisors of 0, because if you consider the product of 2 and 3 with modulo 6, under modulo 6, then you see the result. What is the result? This is k, where what is k? K is the remainder of this usual product on division by 6. Now the product of 2 and 3 is 6, and when it is divided by 6, the remainder is 0. So similarly, we can see 3 into 4. It is also, what is the result? 3 into 4 is 12. 12 when divided by 6 gives remainder 0, and therefore these are the two results we have here. 2 into 3 is equal to 0, but 2 is not equal to 0 and 3 is not equal to 0 till their product under multiplication modulo 6 is 0. Here also 3 is not 0, 4 is not 0, but their product 3 into 4 under modulo 6. This is not usual product. Usually we have this result for this is usual product, and this product we have denoted by dot suffix 6, that is multiplication modulo 6. Remainder obtained when usual multiplication is divided by 6. So these are the results in congruences theory of number theory. And you see this is not for all integers, but here we have these two. And what about 2 into 4 under modulo 6? This is 2 into 4 is 8, 8 divided by 6 gives 2. So this is not an example of a product is 0, but these are the two examples here. Here also 3 is not equal to 0, 4 is not equal to 0. And thus here we can say 2 and 3 are divisors of 0. 2 and 3 are divisors of 0 under modulo 6. And also 3 and 4 under multiplication modulo 6. Similarly, 3 and 4 are divisors of 0 under multiplication modulo 6. So this is the meaning of divisor of 0 or 0 divisor. This exists in C, this set, multiplication modulo 6. Another example we will discuss after defining integral domain, that is set of matrices. This happens in the set of the square matrices. That means the two matrices, if A and B are two square matrices, or we for simplicity we are considering matrices of order second. Their product is 0, but A may not be 0 and B is not equal to 0. So for example, if you consider this set, see 1 0 0 0 and 0 0 1 0, you see the product 1 into 0, 0 into 1, that is 0, again 0, this is also 0, so it is 0, 0 into 0, matrix multiplication, and 0. Now you see, this is A, this is B, and this is 0 matrix O. Till this is not 0, this is not 0. We know 0 matrix, all elements are 0, then it is 0. So this is non-zero, this is non-zero, but their product is 0. So these 0 divisors occur in such type of rings or sets under special multiplication. Here it is matrix multiplication. The multiplication is not usual, but matrix multiplication. So 0 divisor occur in matrix multiplication, 0 divisor occur in multiplication modulo a certain number. And see this also, if the number is prime, then 0 divisor will not occur. Earlier lecture we have studied field, and there we have seen if the Z7 is there, that is set of integers modulo 7, 0 1 2 up to 6, and that in that product multiplication modulo 7, 0 divisors are not there, and therefore see this there will not be 0 divisors. But in Z6, here this is composite number, there are 0 divisors. So there are certain types of sets where 0 divisors exist. And next what we are defined here, is a ring R when a ring is said to be without 0 divisor. That is simple. If 0 divisor does not exist, and there are in many cases, or usually that 0 divisor does not exist, we can't divide by 0. And if for all A, B belongs to R, the ring, if the product A and B is equal to 0, then this implies either A is 0 or B is 0 or both are 0. Then this is the usual case we know for a set of integers, rationals, reals, complex numbers. If the product is 0, product of two numbers is 0, then that must imply either one of them is 0. So this is said to be without 0 divisor, and this is said to be with 0 divisor. Here what is a into b is 0, a is not 0, b is not 0, neither of them is 0. Here one of them must be 0, then we say it is without 0 divisor. So this is the case we earlier known, and this is special case that happens in matrix multiplication and multiplication modulo a composite number. So now we will define what is integral domain. A ring R is called an integral domain. See, if it is, first there are three axioms or properties to be satisfied. If it is commutative, second has the unit element, if it has unit element, and third is without 0 divisor. Without 0 divisor means this property must hold. So if such a ring is there, then that ring is called integral domain. Or simply in one statement, a ring which is commutative with unit element and is without 0 divisor is integral domain. So therefore what will be our examples of integral domain? Now we have seen here this is not an integral domain because there are 0 divisors. A b equal to 0, a is not 0, b is not 0 means there exist 0 divisors. So the set of matrices, 2 by 2 matrices or n by n matrices will not be integral domain because there, see, it is also not commutative. Matrix multiplication is also not commutative and it has 0 divisors. So therefore this is not integral domain. This is also not integral domain, and therefore these are the counter examples. And what are the integral domains? We will see the examples. Simple examples of integral domain are examples. First, the set or the rings of rational numbers, rational, real, or you may consider integers, rational numbers and real numbers, complex numbers, with usual addition and multiplication are integral domains. And that means, see, the set of integers may be denoted by I plus and dot, usual addition, usual multiplication, rationals q plus dot, reals r plus dot, and complex numbers c plus dot are integral domains. And we have discussed these examples earlier. These are rings. These structure form ring. Integers with plus and dot forms ring. What is to be checked is these properties, commutative. Now you see, usual multiplication is always commutative, so therefore it is commutative and has unit element. One exists in each set. I, integers, rationals, real, complex, one exists, and therefore it is a ring with unit element. And is without 0 divisors means for any two elements belonging to these sets belongs to I or Q or R or C. A into B equal to 0 implies A equal to 0 or B equal to 0, and that means it is without 0 divisor. So therefore these are the examples of integral domain. These are infinite integral domains. Now other example of integral domains which is again infinite, that can be considered as a counter example. Just we have seen earlier. Let M be the set of all 2 by 2 matrices with matrix addition and matrix multiplication. Then this set M with matrix addition and matrix multiplication is a ring, forms a ring, or that means this is M plus with and matrix multiplication is a ring. See, this can be checked easily because all the axioms of ring are satisfied by this set of 2 by 2 matrices. 2 by 2 or in general we may consider n by n matrices. Matrices we may consider real matrices or rational matrices. Real matrices means the entries are real numbers. See, matrix with their entries elements are real numbers. It is 2 by 2 matrix, and the general matrix can be denoted as A. See, A, B, C, D. What about this? Or this is the set M. This is the set M, matrix of order 2 by 2, where A, B, C, D are real numbers. That is the set M. And we know matrix addition is closed as sum of two matrices of order 2 by 2 is again a matrix of order 2 by 2. So it is matrix addition is closed, and matrix addition is commutative, that is A plus B is equal to B plus A. Matrix it is closed under plus, that is A plus B is again in M if A, B belongs to M. Then A plus B is in M, that is closure property. This is commutative. For all A, B belongs to M, we are considering A, B belongs to this M, 2 by 2 matrices. And third matrix can be considered as A, B, C. C also belongs to M. Then we have matrix addition is associative. What about the 0 element? O is the matrix, 0 matrix, which is having all its elements 0. So this matrix is the identity for addition, because we have A plus O is equal to O plus A is equal to A again. And what about additive inverse? That is negative A. For A, if A belongs to M, then minus A, negative A belongs to M. 2 by 2 matrix whose elements are negative of the elements of A. Then this is the additive inverse, because A plus of minus A is equal to 0 matrix. So this forms abelian group under addition. Now next we have this dot is closed, that is product of two matrices of order 2 is again a matrix of order 2, and therefore it belongs to M. And further, matrix multiplication is also associative. And one more property of matrix multiplication is it is distributive over addition, from left and from right. So thus distributive law also holds. That means we have A dot B plus C is equal to A dot B plus A dot C. Similarly, B plus C dot A is equal to B dot A plus C dot A. And thus this is a ring. All the 8 axioms are satisfied, and therefore this set of 2 by 2 matrices with matrix multiplication and addition and multiplication forms a ring. Now whether it is commutative, see whether this ring is commutative, it is not commutative, and but M matrix multiplication is not commutative. not commutative. So this is also a reason where it does not form a integral domain. First axiom or first condition fails. But what about has unit element? It has unit element. What is unit element here? It is 1 0 0 1. This is a ring with unity but not commutative. And again, whether it has 0 divisors, so whether it is without 0 divisors, no, it is with 0 divisors, and this is with 0 divisors. Just we have seen example of 0 divisors. It is with 0 divisor. Because this example we have seen, other example can also be constructed. So you may take two matrices such that their product is 0. Their product is 0, but none of them is 0. Here you see this we have seen, and here this is A, B, and is O, but A is not 0, B is not equal to 0. So this is a ring with 0 divisor, and that means we have seen this example as example of a ring which is not an integral domain. Both example we have to study, that example forming integral domain, ring forming integral domain, and ring with which are not integral domain. Then we can understand clear difference between the integral domain and which are not integral domain. So this is an example of a ring which is not integral domain because of two reasons. It is with 0 divisor and it is not commutative. Another example we have earlier mentioned is the ring of integers modulo composite number. This is third example we can consider Z6. Let Z6 be the set of integers modulo 6, 0 to 5 integers, and with addition modulo 6 and multiplication modulo 6. We have seen earlier this forms a ring. Then Z6 under addition modulo 6, multiplication modulo 6 is a ring. This can be easily checked by constructing composition table. We have done this in our earlier lecture of field. There we have considered Z7. Here we have considered Z6. That makes difference. Here 6 is composite number, there 7 is a prime integer. And this is, whether this is an integral domain. Now it is a ring which is commutative, because this multiplication modulo 6 is commutative. We have see any integers multiplication and the remainder obtained when it is divided by 6, that is commutative. And has unit element, it has unit element which is 1. But what about this, whether it is without 0 divisor? No, because we have 2 into 3 under the multiplication modulo 6. We have seen remainder obtained 2 into 3 is 6, and 6 when divided by 6 is 0. That is the multiplication modulo 6 operation or composition. And but 2 is not equal to 0 and 3 is not equal to 0. So therefore it is a ring. It is a ring with 0 divisors. And therefore it is not an integral domain. On the other hand, you note, but see Z7 which will be the integers modulo 7, 0 to 6, and this forms, we have seen this as an example of field, and therefore this is also an integral domain. So we have here, that means the product of any two integers is 0, then 1 is necessarily 0, and therefore it is without 0 divisors, is an integral domain. This is example of finite integral domain. So thus these are the some examples of integral domain. In this lecture we have studied the definition of integral domain and the examples and counter examples of integral domain. I hope you can understand this, and the remaining part we will continue in our next lecture. Thank you.